Number 20 is another interval of convergence problem. We are asked to find what values of x does this power series converge, and we're going to give our reasons. So we first need the radius of convergence. How do we do that? The ratio test. So I set it up right here. Limit as n goes to infinity, a sub n plus 1 divided by a sub n. That's right here. We do the algebra. So as usual, look at what can simplify these 2x minus 1 to the n plus 1 divided by 2x minus 1 to n. You can subtract the power. So you have to the first power, which we can bring this out in front. This doesn't depend on n, so it's like a constant, but we don't know the value of x, so we got to keep the absolute values. Now, these remaining terms we can't really simplify. Okay, so how do we evaluate this limit? Well, we can use L'Hopital's rule. So we would need the product rule on both the top and the bottom. That's what I did right here. All right. And then it's still infinity over infinity, so we can use L'Hopital's rule again. That's what I did right here. Now we start simplifying. We can simplify this complex fraction like this. And if we take the limit as n goes to infinity here, this is just 1. So our limit is absolute value of 2x minus 1. We set it less than 1 because the ratio test says if it's less than 1, it would converge. Okay, so we start solving the inequality. 2x minus 1 is between minus 1 and 1. So x is between 0 and 1 if you do the algebra. Okay, so notice the radius convergence is 1. Okay. Okay. We gotta check our endpoints though, as usual. So we check x equals 0. We plug in x equals 0 into the original guy. We would get minus 1 to the n over n ln of n. So does this converge? Does this diverge? Well, we can use the alternating series test. The big clue was the changing sign, hopefully. We gotta prove that it's a decreasing sequence first. So we can take the derivative and we see that it's negative for n is greater than e. So it's a decreasing sequence. I don't think you have to really show more than that, in my opinion. So this should be good enough. At the bare minimum, you should say it's a decreasing sequence because that's a condition to use the alternating series test. And then we take the limit as n goes to infinity of this guy without the change sign. It's 0. So it converges by the alternating series test. Okay, we checked one of the endpoints, we checked the other. X is equal to 1. If we plug in x is equal to 1, we would get 1 over n ln of n. This, we could use the integral test. There's probably other tests you can do to prove the divergence of this, but I decided to use the integral test. This is a positive and decreasing sequence. We already proved that it's decreasing up here. I don't think we really need to prove that's positive. Hopefully not. Otherwise, the professor really wants you to show every single detail. Okay, anyway, so we evaluate the integral from like e to infinity, 1 over n ln of n dn. Okay, this is an improper integral, so technically you should write it as a limit. So that's what I did over here. And we see that the limit is infinite. So the series diverges by the integral test. So the interval convergence includes 0, does not include 1. And that's the answer for this. So hopefully, if you're following along in this playlist or this practice problem set, you're getting good practice on radius and interval convergence. It's always the same procedure, basically. We first use the ratio test or the root test to get the radius convergence. We start solving for the inequality, and then we check the endpoints. So pretty standard procedure. This is a pretty typical problem.